So it's my real pleasure today to introduce you to Michael Caspersen from Denmark, who will present the best kept secret in programming in education. And just few words about Michael. He is director of the Center for Science Education and associate professor at the Department of Computer Science from Aarhus University. And his research interests are computing education, programming didactics, programming methodology, and object-oriented programming. He also has published more than 50 papers on computing education and is co-author of 2-volume textbooks on programming and co-editor of Reflections on the Teaching of Programming. So I think we will very eager to hear your talk. And so, Michael, the floor is yours.
Thank you very much and welcome everybody. It's really a pleasure and an honor to speak to you and with you, I hope. Yes, I have been invited to speak about programming and programming education, something that is dear to my heart. I have been a teacher for many years, as you can see. I started out teaching when I was just finished a graduate out of university and taught in a non-research post-secondary institution for some 10+ years. Then I came back to university and have been there ever since. In fact, a few things have changed since the description you just gave, Matija. I actually left the Department of Computer Science and became director of something called IT University West, which is a collaboration among the 3 universities in Western Denmark. It's annual funding on the state budget. We have to promote particularly computing or informatics education at university. At the 3 universities in Western Denmark. There's something similar, actually, an entire university, IT university in Copenhagen, which was established at the same time. That's now many years ago, 1999. But so I sort of have given up, and I'm not teaching anymore, just very little. And in fact, the only teaching I am involved in these days is education of future high school teachers, the didactics of computing, informatics, and in relation to that also something about programming education. I was a teacher for many years. I actually did my PhD fairly late in life, after I had been teaching for some 10-15 years. I had a lot of experience teaching. There was something I thought was unsatisfactory, you might say, and I realized that other people thought the same, and therefore programming education became the focus of my PhD dissertation. And it's a number of publications also, of course, on that, but it's really one of the key findings from that work that I will present to you tonight. And when I've used the subtitle of Revealing the Best Kept Secret in Programming Education, the point is that think about a textbook. Of course, I don't know Slovene textbooks on programming, but I know a vast majority of English written in English language textbooks on programming, and they all basically have the same table of contents, right? It's in fact it's not really a book about programming. It's a book about the programming language used to give examples of programs. So the table of contents typically is the language constructs of the language, whether it is Python or Java or C++ or C# or what have you. The table of contents is the various constructs of the language. For every chapter, there is 1 or 2 new constructs presented, and then a number of examples are provided for the students to read. The point is that nobody ever reveals how those programs came into existence. And it has been so, it's a tradition in the way that programming textbooks are written. And it's rather unfortunate if you think about it, because in that sense, the literature doesn't really assist students in learning how to develop programs. They learn about the tools of the trade, but not really programming. So I have, of course, some slides and a PowerPoint presentation. So let me just highlight my points here by sharing my presentation. The first one here. So that's, and I should say, you're more than welcome to, if you can somehow manage to catch my attention and ask questions as we go along. I'm here to hopefully somehow serve you, so don't hold back on that. And I will also make sure that there is plenty of time towards the end also to discuss things. But if there are things on the fly, please don't hesitate to interrupt me. So here is the title. So the point is, here is this small figure, which I call the missing link between the tools of the trade and the products. On the left hand, you have tools, concepts, programming concepts, language concepts, and language constructs, of course. Tools could be the development environments, compilers, editors, typically integrated in one environment, debuggers and so forth, visualization tools and what have you. You have that on the one side, the tools of the trade, and on the other side, the products, the finished programs, which are accessible in textbooks and sometimes also provided maybe by the teacher. The point is the missing link. How does these programs come into existence? By using the tools of the trade and the principles of program development. I decided to have a closer look at that and try to come up with some guidelines or principles or things that could support the teaching of programming. If you think of program in English, it can be both a noun and a verb, a program and to program. But in programming textbooks, it is primarily or maybe even exclusively treated as a noun, a program, a number of programs, those that are presented as examples in the text. This figure is actually from my PhD dissertation, which is now fairly old, relatively. It's, as you can see, from 2007. This is much older. This is a IZZIVI, the ACM Special Interest Group on Computer Science Education, which has existed for more than 50 years. And it hosts every year the Technical Symposium. It's a huge conference, always taking place in the United States. Well, next time actually in Canada, but still Northern America. This is a paper from 1974, so almost 50 years ago. David Grease wrote this paper with the title, "What Should We Teach in an Introductory Programming Course?" And David happened to be my PhD advisor, so there's a relationship here. But let me just read the highlighted section there which is an excerpt from the paper. What do we really teach? We describe the tools the student has at his disposal. His, it is 50 years ago, so that was his. The do loop, go to, declarations, that was the language constructs of the time. Give a few examples and then tell him to write programs. Almost no word on how to begin, how to find ideas, how to structure his thoughts. and how to arrive at a well-structured, well-written, readable program. So the point is, David Griese made this problem explicit, articulated the problem of not really teaching programming, the programming process, the process of developing programs, already in 1974. There were initiatives in the early 70s. I'll come back to that later. Maybe some of you have heard about stepwise refinement. There was some work by really notable computer science pioneers, Edgar Dijkstra, a Dutch computer scientist, deceased now, he died 20 years ago, and Niklaus Wirth, a Swiss computer scientist, the man behind the language Pascal from the 70s. Maybe you have also heard about that, and about Niklaus. Niklaus is still alive. I will come back to that later, but let me just continue with the introduction, because in 2005, there was a conference taking place in the United Kingdom, and it was on grand challenges, an international conference, of course. It was on grand challenges in computing, and there were two strands of the conference. One was on research, and one was on education. And the one on education identified a handful, I think 6 grand challenges in computing education, and one of them was programming. And they articulate here, I have taken, again, some small excerpts from the text. By the way, I should say, I just interrupt myself here, that you will, of course, point 1, have access to my slides afterwards, if you want to, and point 2, most of the visuals in my slides are references to the sources. So here, if you click on the colorful thing on the left, you will get access to the document, the report. There's also a URL at the bottom, as you can see. Anyway, so they write in this text, they write, however, concerns exist among the academic community internationally that when we set out to teach programming skills to students, we are less successful than we need to be and ought to be. The particular concern is that after more than, and this was in 2005, after more than 40, now we can say 55 years of teaching an essential aspect of our discipline to would-be professionals, we cannot do so reliably. Indeed, there are perceptions that the situation has become worse over time. They phrase the challenge related to programming as the need to understand the programming process and programmer practice to deliver effective transfer of knowledge and skills. So that became, I jumped on that challenge. That became the focus of my PhD dissertation. And this is the cover page of my dissertation. It is entitled, as you can see, Educating Novices in the Skills of Programming. There's also the abstract. I don't want to spend time reading this to you, but again, should you be really interested, you have access also to this source of information. I will talk today about primarily one principle, but I would like to mention initially that what is formulated here in, you may know this book. It came out, the first edition of the book, Computer Science Education, Perspectives on Teaching and Learning in School, came out in March 2018, so about 3.5 years ago. It is edited, as you can see, by Sue Sentence from the UK, by Erik Barensen from the Netherlands, and by Carsten Schulte from Germany. It's a book with a number of chapters and contributions by various people. In the first edition, I contributed a chapter called Programming Education, and we have just finished the second edition of the book. It will come out very soon. I don't have an exact date, but the chapter I contributed has been slightly revised, and in the new edition, it is number 18, and the title is Principles of Programming Education. So in that book, I present a total of 12 principles for teaching programming, and they are structured in 4 categories. One is progression, one is examples, one category is about process, programming process, and one category is about abstraction. And the thing I will want to focus on first and foremost tonight is process, that category, process. And there are 3 principles in each of those categories. And the 3 principles under the category process, I call them the reveal, process, and pragmatics. One is called scaffolding through stepwise self-explanations. And the third one is called stepwise improvement. And then the highlighted one here is what I want to focus on tonight. Because stepwise improvement is one way, and I think a reasonable way of teaching programming and teaching students to develop programs, both from a, and that's actually quite interesting, both and first and foremost from a pedagogical perspective, but also from a, should you happen to teach, educate would-be professionals, also from a professional point of view, because it's actually a meaningful way to work as a professional, and the more modern agile techniques for program development very much matches sort of the guidelines provided in stepwise improvement. So this will be the focus of my talk, and eventually what the goal is to support students in understanding the programming process. So what they will experience is not a random walk in some space of trying to find a program solution, but actually we can provide, with the help of making explicit some programming process, a guided tour in that space, and the space is at least the way I will describe it. Actually, I will describe it as a 3-dimensional space, but I will come back to that later. So now I will switch to a different presentation for some practical reason. Don't worry about that. I will just switch over to another. That means I need to stop sharing and then start sharing again. This presentation. So I mentioned the chapter, and here I'm referring to the sort of the current, or I assume old version of the book, and chapter 9, and the 4 categories, they're still the same. In progression, the categories are an advice to be application oriented. You could see more details in the text. Another one is what I call from consumer to producer. You may know this as use, modify, create. That's quite a well-known term for providing progression for students to move through stages where they act as users, modifiers, and eventually creators of software. A third one is complexity of tasks, not complexity of language constructs, as is the typical way things are organized in textbooks. There are some examples. I won't go into details with that. Some on abstraction and patterns, and eventually something about process. And I will touch upon 2 of those principles tonight, just very briefly, the one use, modify, create, and then I will focus on incremental development through stepwise improvement, basically by going through an example. Many of these principles are sort of supporting each other. For instance, some of the principles under the category examples, worked examples, for instance, that's a well-known term from educational psychology, and a very efficient learning means of organizing learning and teaching and learning materials. Works very well with use, modify, create, and with the incremental development through stepwise improvement. Anyway, use, modify, create, you may have heard about this. The students serve first as, or act as, users of software. As you can see on the figure in the upper left corner, The software is not theirs. It's somebody else provided it. It's not mine as a student, but they can use it. They can learn from it. They can read it. They can criticize it. They can test it, and so forth. They can modify it, make small modifications, larger modifications, and so forth, and eventually create new software. There's a number of articles from conferences or from the Inroads magazine talking about use, modify, create. And it's a general didactical principle, because you can use it on many different things, not just programs. You can use it on models, on test suites, frameworks, specifications, and so forth. So a very useful and from my experience, an effective teaching principle. Here I have given a concrete example of how it might be used in the context of programming. First, if we provide a program and some description of what the program is supposed to do, we can ask the students to use the program to test it, see if it works according to the specification, which may just be written in natural language, of course. And if it's broken, ask them to fix it. Then they start moving to the modify stage of use, modify, create. I have here examples of modifications that may be used. The point is here that the modifications that I mentioned are actually preserving the semantics of the program. It still does the same as it used to do, but more efficiently, perhaps, or more nicely, more well structured, with a better design or architecture, whatever. And then the students may start to extend by actually have semantic extending transformations, extend the program so that it does more or something else, and eventually they can write programs on their own. So that was just a warm-up, you might say, as a principle. The one I would really like to focus on is the one which I call stepwise improvement. Stepwise improvement is a small modification of a term that became popular in the late 1960s and early 1970s. It was stepwise refinement. And there is a very important difference between stepwise refinement and stepwise improvement. Excuse me. You may not know stepwise refinement since it's so many years ago, but it was actually very popular in the 70s and 80s. And the critique from David Grease, the stepwise refinement, was like a response to that critique. So there was a lot of tools were developed by educators and presented at conferences, tools that supported this notion of stepwise refinement. Textbooks that were written at the time embraced the notion of stepwise refinement and tried to write about it in the text. So there was a culture in teaching programming in this sort of second half of the 70s and 80s, where the programming process actually was something that was dealt with in many textbooks. Something happened in the late 80s. And what happened was that the world started talking about object-oriented programming instead of structured programming, Pascal and whatever was used as languages at the time. So object-oriented programming came with C++, Smalltalk, Eiffel, later Java, and other languages, of course. And ironically, the methodological aspect of systematically teaching how to develop programs completely disappeared. There's no writing about it in the literature, not in textbooks, not in scientific publications, articles on computing education. But there was a time. So I will tell you a bit about this. This guy here is Edgar Dijkstra. You may have heard about Edgar Dijkstra. He's done so many things, one of the really great pioneers and also a very early Turing Award winner, the Nobel Prize of Computing. So Edgar wrote a paper in 1969. It was called Notes on Structured Programming. It's also published in a book. And in that book, he writes, instead of presenting as a ready-made product what I would call a well-structured program, I am going to describe in very great detail the composition process of such a program. I do this because programs are not there. On the contrary, they have to be made. The basic pattern of my approach will be to compose the program in minute steps, deciding each time as little as possible. As the problem analysis proceeds, so does the further refinement of my program. And in Notes on Structured Programming, Edgar Dijkstra gave several examples of this process, and he named it a stepwise refinement. Because the idea was to start out with an abstract specification of the program, what the program was supposed to do, and then gradually refine that, make it more and more concrete, small parts of it, by breaking down, top-down decomposition and implementation eventually in the programming language. But for a long time, it could be in more abstract code. So that's the notion of stepwise refinement. I'll come back to that also in a minute. But first, I will mention Niklaus Wirth, the Swiss computer scientist that, well, he has done many things, but is probably still most famous for developing Pascal, the first real teaching language of computing. And Niklaus published a paper in, as you can see, in April 1971 in Communications of the ACM with the title Program Development by Stepwise Refinement. And Niklaus simply took Edgar Dijkstra's idea and wrote a very, at least it was at the time, still is a classic paper on stepwise refinement. And in the paper, again, Niklaus Wirth writes, program construction consists of a sequence of refinement steps. Each step, in each step, a given task is broken up into a number of subtasks. So you can think of it as unfolding a tree, and eventually the leaves of the tree becomes the sort of atomic statements of the program, so to speak. So the essence of stepwise refinement, I have tried to describe it here in a picture. So the dark blue thing here, think of that as the underlying machine, so the existing software we have. And then we have a specification, that's the line on the top. And the idea in stepwise refinement is that you start with a specification, a description of what the program shall do, must do, and then you refine that specification, make it more and more concrete, and eventually hit the ground, so to speak, hit the underlying machine. You can then press compile and test if it works. So that's the whole idea. It's also called top-down, for good reasons, called top-down program development. You work from the abstract to the concrete, from abstract descriptions of the program to concrete descriptions and concrete code of whatever language you are using for the task. There are, and you will know many of them, of course, many derivations of this idea of stepwise refinement. There is a theoretical strand of computing research, what eventually became known as the refinement calculus. So some people, and very prestigious people, had huge and successful research careers on developing a mathematical calculus for program refinement, thinking of programs as logic, and combining predicates and program code and so forth. So a formalized approach to stepwise refinement, specifications as programs, calculus for refinement, and so forth. Very, very theoretical approach. What you probably, you may not have heard about this, and it doesn't really matter, but just to mention this, but what you for sure will have heard about is the traditional software development methods, waterfall methods, where there are different phases and depending on how detailed you describe it, you will have a requirements phase, a design phase, a programming phase, a verification phase, and a maintenance phase. And you would go through these sequentially, and you would not go back. I was once involved in a research project with some companies in Denmark, and they just started on developing software for one of their new products. And we said to them, gee, that sounds great. That must be great fun. I mean, you can leave everything, old behind you and start something new. No, they said, no, it's going to take a year and a half until we can eventually start real coding and programming. We need to draw a lot of diagrams and make designs and so forth. And we know that a lot of that will never survive because it will be ideas on paper that doesn't survive when eventually we start implementing things. So these days, waterfall methods are not at all as successful or traditional, much used as they used to be, but there was a time in the 70s, 80s, and 90s. Object-oriented programming changed that, of course. There were specific things called Dijkstra's idea was also called structured programming. There was structured design and structured analysis, and so that whole idea of stepwise refinement really caught on in the community, both in education to some extent, as you can see in research, but also in the industry, in the way people in the industry work with practical software development. There is a story about a battle between two of the old pioneers in computing, Dijkstra, as I have already mentioned, and then Don Knuth from Stanford University in California, where Dijkstra again was presenting an example of his idea of stepwise refinement, and eventually said, this concludes my demo of stepwise refinement, or top-down programming, if you like. Donald Knuth was in the audience, and he stood up and said, yeah, that's right, old buddy, but it only works because you from the outset had the solution in your head. This is not the way that we really develop software if we don't know how to do it, if we have never developed anything like this. It's an ideal way of describing. It's not honest because it's not what we really do. So they had a little battle about that. And I think Don Knuth, to a very large extent, was right. So I'll not share many details with you about how I arrived at this notion of stepwise improvement. I did that by studying experts developing software to see what they were doing, and none of them were using stepwise refinement. Donald Knuth was absolutely right about that. Other people also have studied professionals developing software and came to the same conclusion. What I could see was that they used a different approach, and that's what I call stepwise improvement. So let me present that to you. So I have already presented the idea of stepwise refinement as this top-down development from abstract to concrete. The idea in stepwise improvement is very, very simple. Instead of working top-down from abstract to concrete, we work horizontally by solving a simpler problem first. So if you think of can you see my cursor here moving around?
Yep.
Yes, you can. Thank you. So think of this line here as the specification. So what this shaded area indicates is that I have now solved this part of the specification here. And I have a solution that works for this part of the specification. And I can then take more parts of the specification into consideration, and I can put another layer on my solution here and work here depicted from left to right, but that's of course not important. The point is I work horizontally, and eventually everything will be filled out and I'm done. This is, as I said also in my introduction, both from a pedagogical, but certainly also from a professional point of view, it's honest, but it's also a very efficient and effective way of learning how to program, because these iterations will give you feedback and you will learn in the process. And most importantly, you will have many more chances of celebrating small victories. Let me give you an example in a minute. So I will try to depict stepwise refinement and stepwise improvement in a different way, using this shape I have down here. The dashed lines indicates requirements for the new software. So let me just present to you here first the notion of stepwise refinement. The idea is that you have the requirements, so sort of describing in all of these situations, think of these, the top line here as input situations, possible start states of the program. What should it do? And we want it to end up in the states described down here. And if you work with stepwise refinement, you will have an abstract and more concrete, more and more concrete, more and more concrete, and now it's 100% complete. The point is you cannot press compile until it's 100% concrete. As long as it's abstract, you only have the abstract combined with some concrete. You cannot really test if your idea to the solution works. If you work with stepwise improvement, you can first have a little better solution, a much better solution, an even better solution, and the full solution. So here, the pointy thing here says that for all of these input situations, the program will do what it is supposed to do. There are not many situations in the first instance here, of course, because we haven't made any code yet, but eventually we write code, and in more and more of the input situations for more and more input data, the program will do the right thing. And you have 1, 2, 3, 4, 5, 6, 7, 8 opportunities of celebrating small victories, because now I have a program. It doesn't solve the full problem, but it solves part of the problem. And that's a nice way of working for students. Let me give you a very concrete example. And the example is, suppose that our task is to develop software for this small gadget here. It's supposed to come out for the holiday season, for the potential Christmas gift. So don't speak too loud about it. So the point is that you have this small gadget here. If you press 1, 6, 11, 11, 2022 in the display, it will tell you that it's 16th of November, 2022. And then there is a next button. And if I press the next button here, magically it switches to the 17th of November, 2022. Now, this is just the physical design of the gadget. We need to develop the software to put inside that gadget. How do we go about doing that? By using this idea of stepwise improvement, one way of doing that could be to start out with first to construct the user interface or a part of it with no functionality. That's what we sometimes call all body, no brain. So you have the sort of the physical design of the interface, but there's no functionality yet. So you can press any button and nothing happens. Still, you have the interface. You can show it to potential customers and see if they like it, and they can imagine what should happen, and they can give you feedback on the interface. So that's one partial result. Maybe not that calls for celebration, but still. Then we can make it work, except for the last day of the month. The last day of the month is a bit tricky, but all other days that are not the last day of the month, that's fairly easy, because basically you just need to increase a counter, right? And if you think of it, if we can make it work for all but the last day of the 12th month, we have a program that works in, what is that, 353 cases out of 365. That is something like 97% correct. So we already have achieved sort of in some sense 97% of the goal. We can test it, we can see if it works, we can celebrate it. Then we can assume that there are 30 days in every month. We can ignore everything about leap years and other things, trying to break down the problem and take one small step again for improvement, for stepwise improvement of the solution. And if there are 30 days in every month, it's fairly simple to write the next version of the code, and we will have a solution that works. And actually banks, probably also in Slovenia, certainly in Denmark, they assume 30 days in every month. They calculate interest and so forth. So if the banks are allowed, well, so are we. Then we can make it work for a variable number of days and then concentrate only on that thing that, okay, it's not every month that has 30 days. So some days have less, well, only one, right? And some has more. We can implement that by having a selection statement, some kind of software table, or we can put the number of dates for each month in a data structure and look it up, or whatever, many opportunities for that, different possible solutions. But that's the next step in providing a solution. And the next one we can address, we can think about, okay, now let's address the leap year problem. It's not 365 days in every year. February has a varying number of days per month, of course, depending on leap years. And then there is the special leap year rule. Every 4th century, it's not really a leap year anyway, although it's divisible by 4. So eventually we can reach the right solution, make it work also for those 4 centuries. So in this small example here, you can see that there are 6 steps in reaching. Instead of addressing the entire problem from the outset, as would be the consequence of taking Edsger Dijkstra's approach with stepwise refinement, we here break it up in a number of small improvement steps where we develop a solution to a partial problem, and then we improve, we increase the specification, so to speak, and we put this little layer on top of what we have done already. And here, this is reflected again in this approach, where here is the triangle representing the solution we have after step 1, the all body no brain solution, and then gradually we can improve and improve and improve and reach the solution here. I see a hand in the air, so let me pause. Gregor, you have a comment or question?
Yes, I have a question actually. Thank you for the word. Example is quite nice, but as I see it, actually the students or whoever is going to do that actually has to have some sort of knowledge. Think of it as a, I don't know, a child speaking. The child already knows the words and needs to complete them in a correct order in a sentence. What do you do if the children or students or whoever doesn't know anything of the basic constructs that need to be put here in the correct order incrementally?
There are 2 aspects of your question. I'm not sure whether you are referring to their maybe fragile knowledge of the language constructs, or their they may have a hard time to break down the problem into these, for instance, the 6 steps that I describe here.
Let's start with fragile or non-existent knowledge of the language constructs.
Yes, that's exactly why I mentioned the use modify create principle initially, because before I would come to talking about a programming process, I would make sure that they have a more than fragile knowledge about the basic language constructs. So in the specific programming course that I have been teaching, I don't do it anymore, but I have been teaching an introductory programming course many times, and also more recently, there was a period of 4 weeks initially where I made sure that they had sort of basic understanding of the various language constructs. That is one task. The other thing is their ability to break down a problem and to identify in a stepwise improvement idea, this notion of stepwise improvement, which steps should I take? What should be the first step and the second and the third? How do I break this down into manageable steps? And they cannot do that initially, of course. So that requires help. And typically what I do is that I structure my assignments like this. So I say, here is the task. Now you go ahead and do this, and then you do that, and then you do that, and then you do that. And then after a couple of weeks, and they have seen this for a number of problems, they start realizing this underlying idea. Then we can start talking about it as a principle, and gradually they can. There's a notion also in working with. One of the principles I mention also in the book is something called fated guidance. So well, as a professional and experienced teacher, you will all know it, that you can start scaffolding the students initially, and gradually you step back and they take over because they get the ideas. Some get it quicker than others, and blah blah blah. But it's important to facilitate in a very practical and typically not articulated way this idea of breaking down into steps simply by just designing the assignments. And in my case, it's typically after we have a small practical test after 7 weeks, and after that they have gotten the idea, and that becomes part of the task that they must try to do and get feedback on themselves how to break down the problems. So it doesn't happen like that. I need to help them along the way. Good point, Gregor. Thank you.
One question though, and then I'll
stop. Sure.
You've mentioned at the beginning there is a 4-week phase, if I understood that correctly, when they actually learn the basic constructs of the programming language itself. So doesn't that refer to the thing that you mentioned at the beginning, like every other computer or programming textbook there is, or the content of the
you could say that, except that I actually do it in a more chaotic way, and it works very well. I just use not all, but many constructs, even in the first program they see. But if the program is simple and it does something that makes sense to them, they can digest it. They can appreciate it. They can even question it and challenge it. They cannot do it themselves. But that's exactly where the use, modify, create comes in, because if you provide some, it's very, very difficult to write something from scratch yourself. It's much, much easier to make small additions, modifications to something existing, which you can read and understand. So again, that's why I mentioned the use, modify, create. So those examples initially, it's in a sense, you know, from a traditional textbook perspective, they would be chaotic because they use many different language constructs already in the first example. But it works because the student are seeing the forest instead of the tree or the trees. If you
okay, thank you.
That's my point. Yeah. Matisha, you also have a hand in the air.
Yeah, of course. And what is the influence of the chosen language on this process that you are discussing just with Gregor now? So what is the influence of, let us say, because I think it's quite an important when you present the students with somehow more elaborate example, with more already used constructs, and what is the best language to to use for this?
That's a also a very good question. I do have preferences for some languages over others. For instance, I think it's a criminal offense to teach introductory programming in C++, if I can put it that way. It's like learning to drive a car in a Formula One race car. Those that survives and can manage, they do it well, but we lose too many on the way, along the way. So I certainly have, and my good old friend Bjarne Strostrup, we have many discussions about this. But anyway, the language is not really what matters. It relates to, well, my good old friend and PhD advisor David Grease, he puts it this way. He says, we must learn to program into a language, and you should have your ideas about the structure of the program and the solution described independently of the concrete code, and many the different means of that. But this idea of stepwise improvement, it works irregardless of whether you use Java or C++ for that matter. It's just more complicated with C++ because the language, there are many more language details that you need to address and explain, and the students also can by accident do very unfortunate things, so their program doesn't do what it's intended to do, and it's very hard for them to find errors. So I have been using primarily Java for the past 20 years, but this could be used in JavaScript or Python or C# or whatever. That's not really important. What I do think is important in choosing a language is to have good development tools and good teaching material and textbooks, and that's one of the reasons why I quite like Java as an introductory language, because there actually is probably more than one, but there is a nice book by Michael Culling and David Barnes. It's called Object-Oriented Programming with Java, I think. And it's a book that for every chapter has a worked example where they present an example program, but then they refine it in the chapter and discuss new language constructs. For sure, that's also the structure of their book. But they do present an example which then they refine in the chapter and make it do more or do things differently. So it actually uses the notion of worked examples and not exactly stepwise improvement, but they show how to refine a program and the considerations that goes into refining a program. And also, probably even more importantly, there is a very nice environment called BlueJ where you can visualize program execution and also the structure of the program. There's a nice debugger where you can also look at objects and follow references and objects and so forth. So it helps understand the notional machine, as we call it, also, and those things are, I think, more important than the actual language or syntax or so forth. That's my experience, and you may have other preferences. In general, I think I have experienced for many years that this is almost a religious issue for computer science teachers, isn't it? Isn't that right?
Yeah, I agree.
Yeah.
Okay, thank you.
You're welcome, and then please, as I said, interrupt as you see fit. But actually, this finishes this little example here, or it doesn't quite finish, because I want to show you another thing. I told you about this one coming out for Christmas. If you produce products, you need to have a pipeline of product pipeline. And this one is already in the design for the holiday season in 2023. So the idea is that we now know this little gadget, but you can see that there is room for something more. So we need to add a new functionality, which is previous, which the semantics of if you press the previous button, it goes to the 15th of November. Yesterday, still, of course, the next button must work so that you can go to the 16th and so forth. So the point about showing you this is that if you think about stepwise refinement, this notion of taking the specification from the starting point and then refining that specification to reach a final solution, then in the case of stepwise refinement, it's a new activity. And actually in professional software development, already in the 70s and later in the 80s, software development houses, they had developers and then they have people doing maintenance of software. And those were completely disjoint groups of employees in the company. Somebody was taking care of initial development, others were taking care of maintenance. And essentially, if you think about it, if you have an additional requirement, it's like starting all over again, because now you have a new specification and you need to start out with an abstract solution for that one and then refine it. It doesn't really work. It's complicated. It doesn't fit the framework, the notion of stepwise refinement. But in the case of stepwise improvement, it's just like moving the finish line, 10 meters. If you're running 100 meters and somebody moves the finish line, you may not even notice. Well, if you are very, very experienced in running 100 meters, you will notice, but I would not. I would be dead before anyway. But if you had an additional requirements, it's completely the same ball game. You just add new requirements and you take one more step, and okay, one more step, that's new requirements. So it actually fits very well with practical software development. Same ball game. So I mentioned initially that we can think of stepwise improvement as program development in 3 dimensions. And let me try to explain to you why 3 and what those 3 dimensions are. So in the case of stepwise refinement, it's really a one-dimensional activity because you have a specification, a description. It can be informal, natural language. It doesn't matter how it is expressed. You have a specification of what the program is supposed to do, and then you have your implementation, and it may be just abstract code. Eventually, it becomes concrete. So I have expressed the development process here as a loop. And while this is a while loop, while the implementation does not meet the specification, you refine the implementation, and eventually it is concrete, and you can run it and you're done. But so it is, in that sense, it's a one-dimensional activity. Stepwise improvement, on the other hand, is a 3-dimensional activity because there are 3 things you can do in each iteration. It's the programming process described here as an algorithm. So the one thing you can do as a developer, you can say, okay, if the specification does not imply the requirements, you have the total requirements here. That's the entire line on the top. So that's what I call the requirements here. The part of the requirements that we're currently considering is the specification. Initially, the specification is a very, very small part of the requirements, and it grows and it grows and it grows because we extend it, and eventually it's all of the requirements. So while the specification does not imply the requirements, we can extend the specification. So one step we can take is to say, okay, we draw the curtain a little longer here and say we need to address an additional use case, if you like. Another thing we can do is that if the implementation does not meet the specification, so if this shaded area here does not fulfill what we are currently considering the specification, we can refine this implementation. So refinement is still one of the 3 activities. We can have something abstract that we make concrete, so we can refine the solution that we're currently focusing on. And the third thing that is also a first-class citizen, so to speak, is, I've called it bad smell here. If you have a bad structure of your program, you may need to restructure it. And clearly, if you take another, as I put it previously, if you take another use case into consideration and start developing code to address that part of the requirements, a new part of the specification, you may need to alter some of the code that you have already written. So restructuring is a necessity. It's not because you didn't think right from the start. It's simply because we cannot think of everything all the time, and this is just a realization that you need to restructure sometimes what you have already done. And you can do that because it would not work if you don't do it, or you can do that simply because it starts to become shaky, with a poor design or poor responsibility distribution among the different components of your program and so forth. So there are three dimensions. You can extend the specification to grow closer to the requirements. You can refine your current implementation to better meet the current specification, or you can restructure your program. So in that sense, programming is a three-dimensional activity. And actually, as I mentioned initially, what I did in my dissertational work, I did look at professional software developers, and they actually did this in different ways, but they worked along those three sort of dimensions in different ways for sure, but they were clearly identifiable in the way that professional software developers work. So in that sense, by talking about programming in those terms, we can assist students in not trying to the best of their ability to find their way in the wilderness without any guidance, but actually to help them. And as we already discussed initially, by a lot of scaffolding, because they cannot break the problem down themselves, so they need support in that process. And eventually we can, with faded guidance, step aside and they can take over and do more and more of this by themselves. It's something they get in with the mother milk, so to speak, and they will catch up eventually. So a program can be developed in some steps where you move systematically around in this three-dimensional space and eventually reach a concrete solution which meets the specification. So that's the basic idea of stepwise improvement. And the idea of stepwise improvement, if you think about it, is applicable in many contexts other than programming. And in combination with from consumer to producer, that's the use, modify, create principle I mentioned and worked examples. And I also mentioned faded guidance. You can use it for in our domain of computing, for models, yes, for programs, for entire applications, for interaction design, for so forth. But you can also use it in many other contexts. The Danske Stile you will not understand because that's one thing I didn't get to translate. I see that now. But for physics reports, for instance, in school, for media productions, for music compositions, for social science reports, for many other school subjects, the idea of stepwise improvement is actually quite useful. The students can get feedback on sort of an intermediate result and improve it, or you can actually, instead of giving them the full task up ahead, you can give them smaller tasks to do and gradually improve it and ask them to say, okay, now you have addressed this in your, say, music composition. Now you need also to have a third voice, or we need a B part in the middle, or whatever. You can take your pet subject. When I wrote my my PhD dissertation, you get crazy sometimes in that process. I thought about the process of making the dissertation also as stepwise improvement. So you can think of it in many layers. Anyway, there's a couple of references here. The chapter from the book Computer Science Education with the 12 principles. There's a few other articles and my dissertation, which speaks about some of these things. Should you be interested in more details, I have not talked about Stream. Stream is also a result of, and is described in one of the chapters in my dissertation. It also became a paper in the Transactions on Computing Education, ACM Transactions journal in 2009. Wrote it with Michael Culling, whom I just mentioned. Stream is a systematic way of putting the ideas of stepwise improvement into practice as a first programming process for novices. So if you're interested in more details, that's also a source for inspiration. This concludes the presentation of here we are, the talk about stepwise refinement, and then I can go back to the start and say, I hope now that the title, Revealing the Best Kept Secret of Programming Education, makes a bit more sense. You may not think that well, I would put it differently. Actually, I hope you have revealed this secret many years ago to your students, but I would like to hear comments you might have about this. Anyway, I will stop talking now and leave the rest for you. If you have any comments or questions, I'm sure there are many things we could discuss. So thank you very much for your attention.
Thank you, Michael. It was a very interesting talk. And questions? Does anyone has one? Just unmute yourself and ask Michael. Okay, to break the ice, probably. How your ideas are actually used and accepted among teachers? Especially, I think, the teachers in primary and secondary schools. How is this influenced to this stepwise improvement? Are they aware of it? Are they using it? And how they use it?
Another very both good and relevant question, Matisha. I have two answers. Impact internationally is very poor. Well, first of all, I'm probably not doing enough to promote the idea, but what I also see is that the culture of teaching programming is very strong. People are teaching programming more or less in the same way as they were taught themselves. And it's very hard to change. I have discussed this with colleagues in both internationally in university teaching and also nationally when serving as external examiner. And it takes eventually people embrace the idea, but it takes a lot of interactions and exemplification. It's simply just much easier to do what you always did. The very fortunate and nice thing I have experienced, on the other hand, is that this is completely embraced by high school teachers in Denmark. It resonates so well. I mean, they are not educating would-be professionals. They are educating young people who could go in any professional direction. So they should not be very professional software developers, but they should work with apps, applications, programs, and develop maybe front-end development for a web page or whatever they do. develop a lot of products, and also with the Internet of Things stuff, and you know, and they really embrace the idea. In fact, already in 2010, I think, when the curriculum for informatics in high school was written, there's also a guidelines document, official ministerial document that accompanies the curriculum requirements. And in those guidelines, the notion of stepwise improvement and extension, refinement, and restructuring is actually described as not a requirement, but as something recommended. And it's every year when new high school teachers are educated in the didactics of informatics, that's also part of the curriculum, and they really embrace it, and not simply because it makes sense to them, and that is very rewarding. But an interesting distinction, you know, between colleagues and universities and colleges and high school teachers. So yeah, another good question. And I think
we have here another one coming from David Francesconi, and he asks, do you believe that the approaches you have outlined can also be applied to programming using AI, or could the approach be even different in that case?
I do not have personal experience with programming a specific AI applications, so there could be, you know, additional, you know, finer aspects, but in general, for sure, the approach can be used also in that setting. I mean, my final point about it being applicable also in many other subjects for many other things that you're developing. The notion of stepwise improvement is meaningful. I mean, even if you are preparing a party for your family or friends, you can use the idea of stepwise improvement. So it's really a general problem solution process, I would say. So absolutely, I cannot imagine it not being applicable also for programming using AI.
And did you have any success in explaining, for example, other teachers, especially teachers of other subjects, that this stepwise improvement that students are learned during their learning of programming, that this approach, that this method can be also applied for, like you said, to writing an essay or seminar work or something like that?
Yes and no. I have never tried to somebody who are not informatics teachers, but probably the same thing in Slovenia. But in Denmark, all high school teachers have at least 2 subjects. So they all have a master's degree from university and with dual subjects. So whenever we have new high school teachers in informatics, they will also have another subject. So in that sense, I have in an indirect way been talking to teachers in other subjects, but I have never tried, that's actually a good idea. I have never tried to expose the idea to somebody who's not at all familiar with informatics. An excellent idea.
Because it will be a very slow process if you will wait. For example, okay, now we have an informatics teacher who also teaches history. Okay, now we have one teacher of history who is aware of this method. What about the existing teachers?
One of the informatics teachers who was also teaching Danish and also Danish literature and writing and so forth, she said that actually it's not phrased in the same way, but that idea is also prevailing in the teaching of writing in Danish, something called process writing, she mentioned, I remember. But it's an interesting idea. I think I should challenge myself and target an audience that knows nothing about informatics. I don't have an ambition that the world should embrace stepwise improvement, but I think particularly in informatics, it's a very useful idea. And I think probably the the main argument is that it gives you so many opportunities for feedback and for celebrations. So it's very motivational in that sense. Yeah. So, yeah.
Okay. Any other questions?
So yes, I have one. Somewhere in the middle of your presentation, when we discussed, you've mentioned that you are throwing sort of a chaotic solution to your students. Would it be possible to show us such a solution? I would be really eager to see how it looks like, composed of different basic concepts, and how do they work together?
I can't find it now because I think it's 6-7 years ago since I taught the introductory class last, so I would need to dive into my folder system and find it, but I can describe it to you very easily so you can appreciate it. So one example, first of all, the context of the introductory course I have been teaching most recently is object-oriented programming using Java. So in that approach, I also emphasize the use of baby UML, you might say. Are you familiar with no? So it's just a way of describing in a visual language the structure of your program. So one of the tasks I was asking the students to do was to write a small program to simulate a die cup. If you roll dice, a die cup, and it can have one die or two dice, and you can roll them. And first of all, write a small module that represents a die. You can roll it, and it shows you a face 1, 2, 3, 4, 5, 6. That's a fairly simple solution. I don't ask them to do that. I present the solution with a module representing a die, another module representing a die cup, and the die cup can hold, say, 2 dice, and then they can roll the dice and just see what it gives. Then I ask them to use it, to test it, if it works, if it's the distribution, if it's a sort of a similar number of 1s and 2s and 3s and so forth. So they test that. You can put that into a nice motivating context. And then I ask them to implement the opportunity of having more dice in the cup. And they can say, now I want one with 12 dice or 117 dice or what. So they need to switch the implementation of having just 2 to having some kind of container that can hold all of those, and iterate through the container and roll each of the dice. And in all of that, they use containers, arrays or whatever type of data structure. They use loops, they use if statements, they use classes, modules, they use variables, and they use everything. But it's a simple, well-known problem, so it still makes sense to them, and they can fairly easily solve that exercise. So things like that, where they program something that they know well. They have a lot of experience from their childhood with the concepts and the phenomena, and then the code makes sense to them. I have another example which I would really like to show you, and I can show you that here because that's something very, very different. But that's a relatively new thing that we have only been doing for the past 5 years, and that's with high school teachers. Time is running, but if I'm allowed to just take 5 minutes to show you that example. Yeah.
We are very flexible with time here.
Okay. So let me just see how much I need to say. The logo programming language, that's Seymour Papert's logo and turtle graphics. Is that something that is familiar to you?
Yeah, of course.
Great. So here you are. Here you have Seymour Papert and logo from, I think, 1967. You know Mitzresnik, I'm sure, and he's most famous these days for Scratch. But Mitzresnik was a PhD student with Seymour Papert in the late 80s and early 90s. And Mitzresnik's PhD dissertation was, the title was Beyond the Centralized Mindset. Before I explain the reason for that title, let me show you here that Mitzresnik, he developed a variant of logo, which he called star logo. And the star logo is the clean star, which means you can have not just one turtle, but any number of turtles in your program. And the idea is that these turtles could be of different types, so they could represent different types of objects or agents with different types of behavior. And then you could simulate a part of the world, a system with these objects. And Mitzresnik used that to argue for a way of modeling dynamic systems, which was completely different from the traditional way of doing that. And the traditional way of modeling dynamic systems is with differential equations. It's very, very heavy mathematics. And this is an example of, it's actually a concrete example. The little piece of mathematics you see here is an excerpt from a 40-page document from describing the mathematics of waves. A physics teacher somewhere in Denmark found this document at an American university's homepage, and he also found a document describing how to implement that mathematics in Python. And he managed to make it work, and so he could demonstrate to his students. He didn't have too many of them, but at physics at high level. But he could demonstrate the program to them, but they couldn't do anything with it because, you know, it was complexity, very, very heavy mathematics with added complexity implemented in Python, right? So the point is that if you use the idea from Mitzresnik's PhD dissertation and do not have a centralized mindset and model with a centralized mindset waves, but you do it from a decentralized perspective, you can model the behavior of the individual atomic items in the particles, if you like, in the wave. And you know, we all know that if we hold a piece of wire or whatever, a leash, and you sort of do this with it, and you know it generates a wave, but the waves, the particle doesn't move horizontally, only vertically, and that realization means that if you think of each particle, its x coordinate is constant. If you take the red particles here, its x coordinate is constant, and the y coordinate just goes, you know, up and down. And the best thing a particle can do, if it wants to figure out where to be in the next time frame, is to look at its two neighbors. And that means that if you can add two numbers and divide by 2, the particle can figure out where to be in the next time frame. And that is somewhat simpler than the differential equations on the left, right? So you can actually make a model of waves if you can add up 2 numbers and divide by 2, have thousands of those particles, and then the green generator here on the right, and then you can generate waves. So that's the idea that Mitzresnik and another fellow PhD student called Uri Wilensky had in their PhD dissertations, which came out in 1992 and 1993. And Mitzresnik, as we all know, went on to do something else, but Uri Wilensky stayed in the business of agent-based modeling, as he calls it, and he's now a professor at Northwestern in Chicago. And this whole idea of modeling dynamic systems is very easy in the language that Uri developed. It's called NetLogo. It's very much like object-oriented programming, because you describe the agents or the objects or whatever you want to call them, and their properties and their behavior. And it's very straightforward, as you just saw in the examples with waves. Let me give you another example, quite relevant these days, epidemic modeling. Very same thing. The mathematics of modeling epidemics is, again, very, very complicated mathematics. But if you model epidemics from a decentralized perspective, you can provide very simple behavior for the various people, if it is people being infected, for the people in the model, and you can program that very simply in NetLogo. So for instance, if you have here, the blue people here are receptive for infections. The red ones are infected, and eventually there will be some yellow ones which are now immune because they have been infected and can no longer be infected. So if we start this simulation here in NetLogo, you see that more and more of the blue people become infected, and eventually some of them become immune. And you can also see the curves describing here the persons who are receptive or immune or infected, and particularly the red curve. You probably also saw that many times on Slovenian TV during the pandemic, because there's something about the capacity of the healthcare system and so forth. So you can actually generate this kind of and you can model this kind of systems in a very simple way using computational modeling. And the point is that this may also be somewhat chaotic, because it's not very complicated, but a NetLogo program is like any other programming language, a number of constructs and so forth. But presenting this to the students, it makes sense. They can recognize the context. It means something to them, and they can immediately start modifying the programming and do different things. So this is an example of something they can do. And let me give you another example here, which is modeling a forest fire. In this model, you have very simple agents or objects, if you like. The green ones representing the trees, they follow only one rule. They do nothing. The red is the burning trees. They follow a slightly, once a tree switches from oops, let me just go back here like this. Once a tree is ignited and it burns, it follows different rules. The bad rule is it ignites at neighbor trees, and then it burns out eventually, like becoming infected and then immune. In a sense, it's the same thing, right? So here is an example where we have a density in the forest of 57%. 57% of the ground is covered with trees. And if we start this simulation and we start the fire on the left here, it burns and it burns and it burns and it burns, and eventually it burns out. 12.8% of the forest burns out here. And we can run this simulation repeatedly. Not the same thing happens because the trees are in different positions and so forth. So there's a bit of randomness in this. Here we had 12.8. Here we have what? 12.7. That was almost the same. 9.1, 8. 7.2, 4.4, 8, so forth, repeated simulations. The point is that if we switch, and that's something you can ask the students to do, just to say, now we need another density in the forest. That's very easily not even programmable, because you can move the slider up here, but you can also ask them to do modifications in the code behind the here. Let's see what happens. Well, first of all, what would you think happens? Much more of the forest burns out, actually. Now we are over 50, 55, 60%. Only 4% points more density is still burning, isn't it? 81.5%. And we can repeat it and repeat 75, 84 again, 86, and so forth. The point is accumulating these two experiments with density 57 or 61. On the average, 8.3% of the forest burns out with a 57% density, but with a 61% density, 83% on the average, 10 times more forest disappears in the fire. My point is that this kind of examples, I've been teaching programming for 35 years plus, and for a large part of those years, I tried to find interesting exercises, but that's really the key, to find something that is interesting and meaningful to the students. If you do that, they will go away with that chaotic thing which you asked about, Gregor. It means nothing, because it's interesting. You can dive into this and you can easily understand, at least understand, read the program, and okay, I can trace this and see this is how it works, and then I can start doing modifications. So that's for me, it has been a very different approach to teaching programming for the past 10-15 years, by doing it from meaningful examples that mean something to the students. And as soon as possible, I let them decide what they want to do, and then provide guidance. It's really under some constraints, of course, but it's really important that this motivation is a very strong driver for learning, for working hard and to learn. Recently, I presented this example here in Germany at a conference, and one of the participants in the conference, he wrote to me a few days later. He showed it to his 13-year-old son, and he ran away and programmed this in Python. He knew a little bit about programming, but still 13 years old. And he he had a great time experimenting with this, not in NetLogo, but in Python. So this is examples of and they're not really chaotic, but they're chaotic in the sense that we use the arsenal of tools in the toolbox, but we do it in a simple problem that is meaningful and does something interesting that the students want to play with and want to challenge and work on, refine. In this model, you can say, oh, what if it's it's windy? What if the different types of trees? You get all sorts of modifications to the model. So anyway, I'm babbling away, but this was a couple of examples.
Okay, Michael, we have another question from Uroš. First,
Yes.
He says, thank you for a great lecture. One question: how would you facilitate introduction to programming for young children who lack logical abstract math thinking and are more inclined to humanism?
Could you please read it again?
Okay. How would you facilitate introduction to programming for young children who lack logical abstract math thinking and are more inclined to humanism?
I would find examples. We actually do that in I'm not directly and personally involved, but some of my colleagues are working with kids in lower secondary school, and they have, for instance, examples of somebody mentioned AI in a question earlier, machine learning techniques with biases and other things. So these are, from our experience, something that people with a more humanism-oriented interest are interested in digital technology that reveals some of the things they experience or hear about in everyday life, something that they may experience on social media and other things. So one example that has been developed for lower secondary school is teaching materials where they can experiment with machine learning. Actually, I mentioned initially my visit to Ljubljana a year ago, And at that event, one of your colleagues from the local university presented some really amazing material to teach machine learning. I forgot the name. I can look it up, but you may know who I'm talking about. That was also developed for school kids. So these things that are touching upon biases or other things that are from a human social perspective relevant, that's our experience, that works well. In fact, the curriculum we have developed for primary and lower secondary school and also for high school in Denmark is notable for having both a technical and a human social approach to computing. In fact, what we have done is to combine the more constructive elements of design and programming and computational modeling with a fourth component, a fourth competence that the students must have eventually, must develop. We call it computational or empowerment or digital empowerment, and that's just the term. But what it covers is for informatics what literature analysis is for literature, and what commercial analysis, or movie analysis, media analysis. You know, kids in school learn to analyze literature or to analyze commercials or and so forth. And we also have a component where we teach them to decode, so to speak, to analyze digital artifacts and to analyze their, intentions, both what is by design, but also not by design, but something that happens once the digital technology is put in place. So this additional analytic, critical approach to technology combined with a constructive approach is something that we have very good experience with, because it catches different types of students, but they also realize that if they learn both, they can do, they get, in a sense, superpowers. They can do so much more. It's really a challenge to, I'm working in Europe with this Informatics for All coalition, and we must take this for all. For many years, I have been fortunate to teach somebody who has elected, they wanted to learn computing and programming, but if we really mean it seriously with having informatics as a fundamental subject in school, we must also strive to find ways to motivate and reach all pupils or students, and to teach them something that is meaningful, irregardless of their future career. And I think modeling is one thing that is relevant, irregardless of whether you actually go into engineering or computing or social science or whatever. One of the people we are working with is in archaeology, believe it or not, and she's exceptionally good at agent-based modeling, and she has just recently written a textbook on agent-based modeling as an archaeologist, and just, I think, last year at Aarhus University, archaeology now has programming and statistics as part of the curriculum. So it's coming into human disciplines also. I could give you lots of examples of this, but I think time is running out. Okay, let me conclude with the last question that David posed, and it's a follow-up of his question about teaching programming in AI. Actually, he meant, what is your opinion about OpenAI? So that software that actually writes programs by specification given in natural language. What about, because he claims that no programming knowledge is required, and your main work with your language with 12-year-old pupils. So does David, do you use OpenAI also with 12-year-old?
I can try to explain.
Yeah, excellent.
usually we use OpenAI because it's working just on language. You're programming 2 sentences made of language, and it's very easy to understand for pupils, even if they are 10 years or 12 years age, because
Fantastic.
they easily can understand what is the program doing. We, for the example, in the playground, we have one program that can turn the title from a movie in emoji. So and they can easily understand the structure of how the program needs to receive the order. You have to give the sentence, then 2 or 3 examples, and then the artificial intelligence is understanding what the program need to do, and it start to generate, and you can then mix the intensity of AI. How much does it have to do on its own? And it's very interesting because the access is free for everyone. They give you some credits to work with it and to play, and it's very interesting for the pupils who really don't know nothing about programming, and
I think
it's great.
I think that's a fantastic example, and you're right. I maybe I described. I primarily used this iDate gadget as an example of describing this notion of stepwise improvement. But I would imagine that it works equally well with your OpenAI approach, because the things that they want to program in this very different than from the traditional point of view way of programming. The notion of stepwise refinement, or sorry, I should not make that mistake. Stepwise improvement also is meaningful for that type of for that approach to programming, and yeah, you touch upon a very interesting thing. People say, well, maybe we don't need to teach programming anymore because we can. The systems can be developed in different ways, but to me it's still programming, even though it's not the traditional, syntactical modification of source code, but you're still programming. You're still specifying to the computer some kind of constraints for the computations that you want it to be able to do, and from that perspective, to me it's still programming, and therefore I would also think that the notion of stepwise improvement is a meaningful approach to developing applications of systems or software. But it sounds like a great thing to do, and I would really love to read or hear about it. So if you have an event where this is on the agenda, please let me know.
Yeah, I believe that with those kind of programming, your approach will be even more necessary, because they won't be able, they don't need really to know the code, but they have to structure their way of thinking about programming.
Exactly. Yeah, very good point, David. That's an excellent point, actually. I never thought of it that in that context, but I like it. Thank you for your comment.
Okay.
Thank you for the lecture.
Any other questions for Michael? Okay, if not, I wish to express my really great gratitude to Michael for his excellent presentation, and I also hope you will send me slides, and we will publish them in our Moodle that we have a special subject just for this series of webinars, so that participants can get their slides in our Moodle.
Excellent. I'll do that right away, and thank you very much again for your invitation and for your interest. It's been a pleasure.
It was
really nice presentation.
Thank you.
Thank you, everybody. And you take care.
Bye.
Thank you.
Bye.
Thank you.
Bye-bye.
Bye.
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 Night.
Bye. Thank you.
Bye. Thank you.
Okay.
Thank you. Bye-bye.
Bye.
Thank you. Bye.